This video is about simulation for model checking. So we talked a little bit in the early couple of weeks about how to simulate data, say from a standard distribution like the normal distribution or the Poisson distribution. But in general, you might want to do slightly more complicated simulations to be able to check your models or to be able to sort of validate your results and see if the sort of analysis procedures that you're using are reasonable. So the basic ideas here are to use the sort of R-foo, so R-norm or R-Poisson sort of random variable generators, but to generate them in the context of a statistical model in order to be able to sort of evaluate different analysis procedures. So simulations can be very flexible and useful. So for example, we saw how they could be used for bootstrapping in week 7, but they can also be used for evaluating models, for testing different hypotheses, for sensitivity analyses, or for prediction like we saw with the predictive models. So at minimum, it's useful to simulate a best case scenario and a few examples where you know your approach won't work so that you can get an idea of if your sort of analysis approach fails on the best case scenario where everything holds to exactly your assumptions, you know that there's something gone wrong. And then you might want to have a few examples where you know your approach won't work so you can kind of understand what are the boundaries of which assumptions are really critical and which assumptions aren't that critical. Because a critical assessment of the assumptions behind your statistical modeling can be very useful for making decisions on the basis of your analysis. I wrote a little blog post just recently about this called The Importance of Simulating the Extremes, which I've linked to here as well. So in terms of simulating data from a model, I'm not going to go into too much detail on this because this has actually been covered previously in Roger Peng's lectures for computing for data analysis, which you can find on YouTube. But suppose that you have this regression model where yi is the outcome and you have an intercept term plus a slope term times the measurement for the x variable xi plus ei, where xi is the covariate that you're interested in and ei is everything, a representation of everything we didn't measure. An example of how to generate data from this model is you can generate xi and ei to be normal random variables using the R-norm function, just like we learned earlier. So we set the seed so that we get the exact same simulated results if we run this code again. And then we generate 50 normal random variables using the R-norm command, and by default this generates normal random variables with mean 0 and variance 1. We do the same thing for the E variable, and then we set our coefficients. In this case, we're going to set the intercept to be equal to 1 and the slope to be equal to 2. And then we just construct our Y variable, or our outcome variable, according to the actual regression model that we've assumed here. So in this case, we've assumed this regression model. Then we generate data directly out of that regression model. And that way, we can use this to evaluate whether the regression model is sort of a reasonable fit or not a reasonable fit to the data. Something that's a very good thing to think about is, so in general, if you generate data from a model and then fit that model, you'll get a very good fit. I mean, it sort of makes sense. But one thing to evaluate is whether a violation of your assumptions might lead to differences in sort of your statistical analysis. So here I'm generating again from the same regression model, but I'm going to actually generate two different types of error terms here. E can be either normally distributed, which is sort of the standard assumption for linear regression, or it can be Cauchy distributed. So the Cauchy random variables are actually random variables that have a much fatter tail. In other words, there are a much larger number of large values when you generate from a Cauchy distribution, as we'll see in a minute. So again, in both cases, I'm going to set the intercept to be equal to 1 and the slope to be equal to 2. And then I generate two different sets of y variables that have the exact same sort of component that is the intercept plus the slope times the x values. But then I add two different error terms, the normal error terms or the Cauchy error terms. So if I do that, then I can plot from the linear model, I can fit a linear model relating y to x. So remember, y is the data that was actually generated from this same linear model. So you'd imagine that the fit would be pretty good. And I can plot the fitted values versus the residuals. So this is, again, one of those model checking plots that you might make. And so in the case of normal errors, you see sort of exactly what you'd expect to see, sort of a cloud of points with no real relationship. In the case of the Cauchy errors, remember we simulated exactly from the regression model, just added a different kind of error term. And in this case, when we plot the fitted values on the x-axis versus the residuals on the y-axis, you see that at least a couple of the residual values are actually very, very large. So this suggests that our model isn't fitting very well for a small number of these observations. which suggests that there sort of might be some trouble with our model fitting. And so, in general, when you're doing simulation analysis, particularly for evaluating whether your assumptions are met or not, it's a good idea to repeat the simulation more than once so you can get an idea of the variability that you might expect to see from in different studies. So in general, when you're analyzing a data set, you only get to observe that one data set. But by doing simulations, you can observe a bunch of different kinds of data sets and see how you would get slightly different answers if you got different data sets. And that can give you an idea of how robust the answers you're getting are in your individual data set. So again, here I'm doing the same thing. I'm generating x values and e values. The e values are generating either from a normal distribution or from a Cauchy distribution. I'm setting the intercept to be equal to 1, and I'm setting the slope to be equal to 2. I'm doing this 1,000 times, and each time I generate a new y and y2. So these are two different y variables generated from two different models with two different error terms. And I calculate the actual regression coefficients in each of these 1,000 simulated data sets for the normal errors and for the Cauchy errors. And so then if I look at the quantiles of the regression coefficients that I get for the slope with normal errors, you can see that they're centered around 2, which is good because I generated data that had a slope of 2. And they have a sort of a reasonable variation. They range from 1.5 to about 2.5 in terms of the estimates in different studies. So again, the variation we see here is across repeated samplings of different studies, not the variation that you'd expect to see sort of from an individual sample estimate of the standard deviation. And then we can do the exact same thing, look at the quantiles of the estimates that we get when there's Cauchy errors. And in this case, again, they're centered around 2. You know, it's 1.965 is relatively close to 2. But here we get estimates that can be wildly different. So for example, we might get an estimate as low as minus 278 or as high as 272. So having these fatter-tailed error terms can lead to dramatic differences across repeated studies in our beta coefficients. And so if we believe that the error terms are closer to Cauchy than they are to normal, you can imagine that that might lead to high variability or mistrust of the beta estimates that you get from our regression modeling approach. So another thing that you can do is look at a box plot of these values, and so you can see that the values for these are the beta estimates or the slope coefficient estimates that we get across 1,000 repeated samplings. And you can see that they're sort of tightly clustered here around 2 when the errors are normal. When the errors are Cauchy, you can see you get wildly different estimates of the beta parameters, and in fact this goes way off the screen, both above and below, down to minus 278 and positive 278 or so. But this gives you an idea of how much more variable your estimate would be if you have a change in the sort of model assumptions in terms of the error distribution that you're using. This variability that we're estimating here is what's called Monte Carlo variability. The Monte Carlo variability is what you get as the estimate of, like, if you do more and more and more simulations, you'll get more and more accurate bounds on what this variability will be. So in other words, if we increase the number here from 1,000 to 10,000 to 100,000, you'll get a better and better idea of how variable these numbers will be, and we can reduce the Monte Carlo error by just increasing the number of samples that we collect. So another thing that is important when performing simulations is often to try to mimic the data that you actually have observed in some respects. So you don't want to exactly reproduce the data that you have observed, but you might want to take some of its characteristics into account when you're generating simulated data to evaluate modeling assumptions. So here again, I'm going to load the Galton dataset, which is in the using R package, and I can get the number of observations in that dataset. And then I can make a histogram of the child heights. So in this case, the data are the heights of a large number of children and the mid-parent height or the average height of their parents. And so you can see the distribution of child heights here and the distribution of parent heights here. And so you might want to try to create a simulation that would simulate new children and new mid-parents. So one way that you could do that is to generate data that come from a similar model to the model that you've observed in the actual data. So here what I've done is I fit a linear model relating the child's heights to the mid-parent's heights. So the outcome is child height, then the tilde separates over here the covariates, in this case the parent height. So then what I'm going to do is generate new parent heights from a normal distribution. Because this distribution here looks relatively normal, I'm going to generate new parent heights from a normal distribution. I'm going to generate it with the same standard deviation as the parent heights in the original data set and the same mean as the parent heights in the original data set. Then I'm going to generate child heights directly from this same linear model. So I've got the coefficient estimate for the intercept and the coefficient estimate for the slope, which I multiply by my simulated parent heights. And then I add noise or measurement error, which is going to have the standard deviation equal to the amount of variability that you would observe in the residual variation after fitting the linear model. So then what I can do is I can plot on the left here, this is the actual observed data, so on the x-axis is the parent, mid-parent height, the average parent, and on the y-axis is the child height, and you can see this sort of cloud-shaped point with this relationship. And this is the new data that I've generated. So again, this is parent height, mid-parent height on the x-axis and child height on the y-axis, and these are actually just now simulated made-up values, but you can see they have a very similar relationship as the values that you have here in the original data set. So we can generate a bunch of new data sets using these parameters, and that will give us an idea of a way to evaluate sort of our modeling choices based on data that sort of mimic the properties of real data. So now I'm going to give one more example just to show you an example of something a little bit more complicated that you might want to simulate, just to give you a flavor of how you can build simulations around more complicated scenarios as long as you're sort of thinking about what are the key properties I want to mimic. So in this case, I've loaded this stamp data. So this is the thickness of a large number of stamps from a particular year. And so you can see a histogram of those stamps. So you can see that they have a variety of different thicknesses. And then I've actually overlaid here a smooth density function over top of that. So this is the smooth density function representing those same thickness values. And so one thing that you might want to do is generate new stamp values, say, that mimic some of the properties of this data set. And so the first thing that you might want to do that might be a little bit too simple or too simplistic is if you could plot sort of the density of the original data set, that's in black here with these two sort of little bumps. And then what you could do is just generate new thickness values that have the same length as the original data set, where they're just normally distributed random variables with the same mean as the original data set and the same standard deviation as the original data set. But you see here that this actually is slightly too simplistic in that you get simulated data sets. Each one of these density lines, gray density lines, represents one new simulated data set. And you can see that they all look like sort of normal distributions, and they're missing this key characteristic of the original data set, which is that there's at least these two sort of modes or two humps in the data sets. So to mimic the data a little bit more closely, we could go back and look at actually how that density estimate was calculated, and that might give us some ideas about how to simulate. So on the left here, we see a histogram of a set of data values. These aren't the stamp values. These are now just a new set of values that come from this plot, which I found on Wikipedia. On the right side is actually the density plot for this same histogram. And so each of these black lines here at the bottom represents a data point. So in this case, we have 1, 2, 3, 4, 5, 6 data points. And at each data point, we can actually draw a normal distribution that is centered at that data point, where the standard deviation is a fixed value for each of these little normal distributions. Then what we can do to get the estimate here at this point, we just add up the value for each of these 6 normal densities at this x value. So for example, this x value, you get this much from this density, this much from that density, this much from that density, and this much from this density, and so that you end up with a relatively large value because a lot of densities overlap this particular x value. Alternatively, if you go out here, say at -5, all of the densities have low values here, so you add up this value plus this value plus this value, and you get a smaller value of the density. So this sort of adding up smaller density functions to get the larger density function is what a kernel density estimate does. So in general, it uses the normal distribution as a default distribution here. So you can imagine, since we're actually using these normal distributions to estimate this smooth line, an alternative is we could just simulate data where the data is drawn randomly from one of these small normal distributions. And in fact, that's a very reasonable way to simulate data from the same distribution as the SAMP data. So first we're plotting in black the originally observed data with the sort of characteristic two bumps. And then what we're going to do is generate a new set of observations where each observation is drawn from a normal distribution with the mean equal to the thickness of one of the originally observed stamps, and the standard deviation equal to this bandwidth that we get from the original density estimate for the original data. The bandwidth is actually defined as the standard deviation of the small little normal distributions that you were going to add up. So what we're getting here are a set of normal random variables that are drawn from those smaller normal densities that we added to get the density function. If we make a gray line for each of these new observed data sets, we see that they now mimic a little bit more closely the originally observed data, and they're actually quite tight. In other words, most of these distributions look very similar to the originally observed data. So we might even think about adding in a little bit of extra variability if we believe that this is maybe a little bit too closely matched to the original data. So one thing that we might do, say for example, is generate variables that have the same means as the original thicknesses, but where we've increased the standard deviation by some fraction, say 50%. So then we see that there's starting to be a little bit less of the two bumps that were originally clear, but you see the data are a little bit more variable. This allows you to sort of evaluate different potential models for the observation of the stamp data that we've collected. So I hope that gives you a little bit of an idea about how, in this particular case, how you would generate data from a more complicated distribution, in this case this empirically estimated density function. But you could imagine doing this for all sorts of different scenarios where you have a more complicated estimation procedure, and using that estimation procedure you can sort of define how you want to simulate data. So simulating data can be applied to missing data problems, so you can imagine simulating different ways that the missing data might occur. And so there's actually a large literature on this problem and is worth looking at in specific multiple imputation. Simulation values are often drawn from standard distributions, but this may not always be appropriate. So for example, with that density example, we actually didn't want to just generate from a normal distribution. We had to do something slightly more complicated. Sensitivity analysis in general means trying out a bunch of different simulations where different assumptions are violated and seeing how the estimates that you get change. And it's important to perform sensitivity analysis even if you're performing standard applied analyses to be able to evaluate whether those analyses will produce very different results if just one or two of your assumptions break down. There's a very nice section on simulation in the advanced data analysis from an elementary point of view. And then I've linked here to a set of handouts and to a very nice paper that describe how to set up simulation studies in statistical analyses.